Hey math fans, Alex here, and I'm coming with you with Chapter 3 of Probability Theory. So this section is on conditional probability, which is an extremely important concept. And the main question that we want to ask in this section is, given events A and B, how does event A affect the probability of B occurring? So we're going to establish what independence means mathematically, and we're going to use that for a lot of important theorems later on. Okay, so to motivate this definition of conditional probability, let's kind of look at the following example. Okay, so suppose that, 30% of a population enjoys rock music. Okay, and we'll say 55% enjoys pop music, and we'll say that 5% enjoy both. Okay, so let's sketch out kind of a Venn diagram of everything that's happening here. Okay, so we have the total population, or the universe, the universal set. And then we have two situations, the realm of rock music and the realm of pop music. I, of course, belong in the intersection of the 5%, and you should honestly start with the 5% every time you're doing a problem like this. So this is the 5%. And then a total of all 30% is going to enjoy rock music. So that includes this 5%. So the people that only enjoy rock music amounts to 25%. Okay, likewise, the people that only enjoy pop music is going to be the 55 minus the 5%, so we have 50%, like that. And then when you add all of that up, this plus this plus this, you're going to get 80%, which means that there's 20% that enjoy neither. Now, here's my question. My question is as follows. What's the probability? What is the probability that a rock fan enjoys pop music? What's the probability that a rock fan enjoys pop music? Well, naturally speaking, we're given information about the sample, and that information is that the person is already a rock fan. Okay, so the individuals that are neither a rock nor a pop fan, as well as the people that only enjoy pop music, they're excluded from our population of interest. Our population is now changed to only be people that enjoy rock. Okay, so out of this circle right here that I drew, what's the probability that people in that little circle enjoy pop music? Okay, and logically speaking, it should be out of the 30%, or out of the 0.3 total from this entire circle right here, we're only interested in the people that also enjoy pop music. And the only people that are going to enjoy pop music that also enjoy rock music is the 5%. Okay, so when you do that, then you get 1/6, which is actually the correct answer. Okay, so hopefully that kind of motivates a definition, which we're going to make right now. So we're going to go ahead and define the conditional probability We're going to define the conditional probability of an event A given that event B has occurred. Okay, given that event B has occurred as follows. We're going to say that the probability of A given B is going to equal the probability of A intersect B, all divided by the probability of B. Okay, where this symbol right here is referring to, given that B has occurred, this symbol. Okay? And if you plug in our example, that's exactly what you get right above, because 0.05 is the probability of rock intersect with pop, and the 0.3 is the probability of just rock. Okay, so this definition kind of makes sense, but we do need to talk about a couple of important aspects. So note, so warning, is that this is not the same. This is not the same as the, I guess, regular or usual definition of probability. Okay. Why is that not the usual definition of probability? Well, recall that the usual definition of probability, if we have an event A, so the probability of an event A occurring is the number of ways that A can happen divided by the total number of outcomes. This is not the same thing as that. Okay? So we kind of have to treat this different from regular probability, but as it turns out, defining it this way, it's going to have a lot of symmetric properties with the usual definition of probability. And also, it is worth noting that the probability of A given B, which, remember, by definition was the probability of A and B divided by the probability of B, these are each probabilities in their own right. And the definition of probability says that this would technically equal the probability of, the number of ways that A and B can occur divided by the total number of outcomes. That's the numerator. And the denominator would just be the number of ways that B can occur divided by the total number of outcomes, right? Okay, but then these cancel, and we're left with this somewhat odd interpretation that the probability of A given B is the number of ways that A and B can occur divided by the total number of ways that just B can occur. So clearly this is not the same as this, but if we kind of treat it as the same, then we get a lot of interesting properties. Okay, so here are the properties of conditional probabilities. The first one just says that the conditional probability, just like regular probability, is a number between 0 and 1 inclusive. But what's more is I can tell you exactly when it's 0 and exactly when it's 1. Okay, so if the intersection of events A and B is empty, in other words, they're mutually exclusive, well, then the probability of A given B is equal to 0, okay, because they can't occur at the same time. Okay, if B is a subset of A, or in other words, if B implies A, that means that the probability of A given B is just 1. And lastly, probably the most important, is if you have K mutually exclusive events where the event A can be broken up into essentially a disjoint union of those events, well then the probability of A given B is now a sum, just like it was for regular probabilities, but this time it's a sum of conditional probabilities. So it behaves exactly as you would want it to behave. Okay, now we're going to go ahead and prove these. Okay, proof. Okay, so for part A, all we have to do is note that A intersect B is a subset of B, right? A and B. If something is in A and it's in B, that implies that it must be in B. Okay, and if you recall, one property of probability is that if one event is a subset of another, that implies that the probability of A intersect B is going to be less than or equal to the probability of B. Okay, but since probability is a number that's greater than or equal to 0, then we have that 0 is less than or equal to the probability of A intersect B, less than or equal to the probability of B. And then all we have to do is divide everything by the same thing. We're going to divide it by the probability of B. And since the probability of B is a positive number, we are allowed to do this without swapping any inequality symbols. Okay, well, this number is 0, right? This is the definition of conditional probability. And this is 1. Okay, so that proves part A. Part B, well, remember that the probability of A given B is, by definition, the probability of A and B all divided by the probability of B. And we're trying to show what? We're trying to show that if A and B are mutually exclusive, then this conditional probability has to be 0. Okay, but mutually exclusive means the probability of A intersect B is 0, and who cares what the probability of B is? That's just 0. Next, we have to show that if B is a subset of A, that implies this conditional probability is 1. Okay, but first, a little claim. The claim is, if B is a subset of A, then A intersect B has to be B. I mean, just think about it. If you have a set inside another set, then if you intersect those two, well, the only overlap is just going to be this smaller set. Okay, but I'm going to leave that as an exercise for you to prove that. Just a little basic exercise in set theory. Okay, but given that relationship then, we can again write the probability of A given B as the probability of A intersect B divided by the probability of B. Okay, but these are clearly the same, which means that this is just equal to the probability of B divided by the probability of B, which is 1. Okay, last but certainly not least, part D. So we're going to go and write A as a union of disjoint events with the AKs mutually exclusive. Well, first thing to note is that A intersect with some event B, by definition, is going to be this union intersect with B. Okay, but there's some sort of distributivity that I think I talked about in an exercise from last chapter. So this B is essentially going to distribute into the union. Okay, so this is going to get us a union. The union structure still stays there, but then we're going to have AK intersect with B. Right? Okay, so what does that mean? Well, it means that the probability of A intersect B is just the probability of this union. Okay, but we already know what the probability of a union is, provided all of the events were disjoint. Right? That's just the sum of all these, the probability of those occurring. So that's the sum of the probability of A sub k intersect B. Okay, so thus the probability of A given B occurring, which is just the probability of A and B divided by the probability of B, would be the sum AK intersect with B divided by the probability of B okay, but this probability of B can distribute inside the sum so that each of these are being divided by it. And that's just the definition of conditional probability. So this is just the sum K of the probability of A sub k given B, which by definition is the probability of A sub k intersect B divided by the probability of B. Alrighty. Now, suppose we are trying to find some probability of A, and we aren't really given the number of ways A can occur over the number of total outcomes, because like I mentioned last chapter, those can be incredibly difficult to find or calculate. So, what do we know? Well, suppose we know that B sub 1 through B sub k is a set of mutually exclusive events. And then whose conditional probabilities with A, i.e., the probability of A given B sub k for each k is known. Okay, so we're kind of flipping it. Instead of A sub k given B, well, now we know we're trying to find probability of A given that some possible event out of the total B events occurs. Okay. Well, what happens then? So what happens? Well, we know that A can be written as A intersect with the whole universal set. Right? Because if you take the entire universe and intersect that with just A, well, you're going to get just A by the exercise above. And the whole universal set is just going to be the union of all the B sub k's. Right? We're assuming that it's a set of all mutually exclusive events, and those are all the ways that B can occur. Okay, so if you union all of those different partitions, then you get the universal set. So you're splitting the universal set up into B sub 1, B sub 2, etc., all the way up to B sub k. Okay, and then just like before, this intersection is just going to distribute. Okay, so this is just going to be still a union, but this time it's going to be A intersect B sub k. So, hopefully this looks similar to the proof of part D of the properties. So the probability of A occurring is just going to be the probability of this union occurring. Okay, but these are all disjoint. Okay, so this is just going to be the sum over k of the probability of A intersect BK. Okay, you might think to yourself, well, that's not really conditional probability. Well, why not? Well, you need to divide this by the probability of B sub k occurring. And I couldn't agree more. So let's just do that. Let's just force the probability of B sub k to be on the denominator. Can't do that for free, though, so you also have to multiply by the probability of B sub k. And then we get that the probability of A occurring is the sum over k of the probability of A given B sub k, by definition of conditional probability, times the probability of B sub k. And this formula is going to be extremely important for us. Because believe it or not, the way that an event can occur could happen in multiple different ways that partition our universal set, and these conditional probabilities are really going to be valuable. And to end off, I would just like to do one example of where this is useful. And you're going to see by the end how exciting this is. So example 1, I'm actually going to do a part A and a part B, so we'll just do example 1, part A. All right, so here's our example number 1, part A. It says a hiker leaves the point O, shown on the graph below, choosing one of the roads OB1, OB2, or OB3 at random. Then he chooses another road at random. Okay, so if he's at OB1, then he could choose either this one or the one that I, of course, forgot to draw in, which would be this one. If he's at OB2 right now, he could either choose this road or this road. And if he's at B3, then he can either choose this one or this one. Again, all this is at random. So then what's the probability of the hiker arriving at the point A? Imagine it's a hiker that's just completely lost and has no sense of directions when it comes to the roads. Only mountains is what he knows. Okay, well, we're going to go ahead and define an event just like we always do. We're going to go ahead and let B sub k be the event that the hiker passes through the point B sub k, where k is, of course, either 1, 2, or 3. And then, you know, B1, B2, and B3 are a set of mutually exclusive events, right? Why are they mutually exclusive? Well, the hiker can't travel to B1 and B2 at the same time. And that's all he can do. There are no more events in this universal set. It's either B1, B2, or B3. Okay? And since they're mutually exclusive, they also occur with the same probability. So the probability of B sub k is what? Well, it's 1/3. Number of ways that could happen divided by the total number. For a given B sub 1, B sub 2, or B sub 3, it's going to be 1 divided by 3 total possibilities. Okay? So again, we want the probability of A occurring. Let's just scroll up to our fancy formula. We already have the probability of the B sub k's. Now we just need some conditional probabilities. Okay, so let's find those. Okay, so we have that, you know, the probability of A given B sub 1, for example. Well, let's just see. If B sub 1 happens, then the hiker is right here. And then what's the probability of getting to A, given that that has just occurred? Well, hopefully you say 1/2, right? There are 2 roads, one going to A, one not going to A, so that's pretty easy. It's 1/2. Actually, if you look at all these other possibilities, if he's at B2, it's also similarly 1/2, and if he's at B3, it's also 1/2. Okay, so we have that probability of A given B sub 2 is 1/2, and the probability of A given B sub 3 is 1/2. If you think this example is boring, I promise it gets more interesting. Okay, so thus the probability of A, which is just the sum from k equals 1 to 3 in this case, of the probability of A given B sub k times the probability of B sub k. Well, the probability of B sub k is a constant because it's always 1/3, so I can kind of pull that out. And then we get, well, probability of A given B sub 1 plus the probability of A given B sub 2 plus the probability of A given B sub 3. So we have 3 1/2s, and we're taking 1/3 of that, so we get 1/2. Which again is not surprising because you can actually enumerate all of the possibilities of all paths traveled, right? And you'll find that there are 6 paths, and 3 of those paths will lead to A. Okay, so getting 1/2 is not really surprising. But now let's look at the second part to this question. I think you'll be a little surprised. Okay, so now let's look at the example. Okay, so after arriving at B1, B2, or B3, now instead of randomly choosing one of the paths, the hiker will always choose the path that creates like the sharpest change in direction. Okay, so what that means is here this is a little bit more gradual, so the hiker is always going to choose this path. Here if he's at B2, he's going to choose the most straightforward path, and here at B3 he's always going to sorry, not the what am I saying? He's going to choose this path because it's the sharpest change. Then if he's at B3, he's going to choose the sharpest path. Okay? In other words, he always kind of changes the direction the most. Now what's the probability of getting to A, given that he's always looking for like the sharpest change in direction? Okay, well, that's, again, not terribly difficult, right? The probability of B sub k occurring is still 1/3. But this time, what's the probability of A given that B sub 1 has occurred? Okay, well, if B sub 1 has occurred, then the probability of getting to A, well, given that he's always looking for the sharpest change, he's going to go to A anyway, regardless. So his decision choice makes this probability just equal to 1. Okay, now if he's at B2, what's the probability of A occurring given that B2 has occurred? Well, he's going to look for the sharpest change in direction, so he's always going to choose this path, so that probability is equal to 0. And what's the probability of A given that B sub 3 has occurred? Well, again, he's looking for the sharpest change in direction, so he's not looking for this path, he's looking for this path. And since that's going to A anyway, this probability is just 1. So that means that the probability of A is equal to the probability of, or it's equal to, the sum from k equals 1 to 3 of the probability of A given B sub k times the probability of B sub k. Well, just like before, we can factor out that 1/3, and this just becomes 1/3 times the sum, the probability of A given B sub 1, plus the probability of A given B sub 2, plus the probability of A given B sub 3. And we get a probability of 2/3, which is higher than what we had initially, which was 1/2. So it looks like always changing directions was the right move in this case. Remark, oh, by the way, this proves the famous Monty Hall problem. So, if you're unfamiliar with the Monty Hall problem, game show host has 3 doors, and behind 2 of the doors, he puts goats or zonks or whatever, and behind here, he puts a fabulous prize. Okay, so the contestant picks one of 3 doors. And then after the contestant selects their door, then the host decides to remove one of the non-prize doors. Well, at this point, if you selected this door, the only possible door the host can remove, he can't remove your door, so he has to remove this door, which is why there's no path going to that door. If you choose this door, well, then he's randomly going to choose to either remove this door or this door. I chose that he removed this door, which means that your only options are here and here. And if you choose this door, likewise, he has to remove this door, which is why those are the only 2 paths. And the question is, if he removes one of the doors, should you stay where you are? In other words, should you just go along the intended paths? Or should you change doors or make a sharp change in direction? And not only did we figure out that it's wiser to choose to switch doors, but we actually calculated exactly that the probability of success with always switching doors was exactly 2/3, which is the answer to the Monty Hall problem. Thanks so much for watching. Hopefully that helped you out.